Hello everyone, in this recording I wanted to share a few tricks that I think are often useful when working with geospatial data, but which don't fit into one of the larger categories that we study so far in this course. So the first trick. Often when working with a geospatial problem, the data are not stored in an explicitly geospatial format, right? So you might have a data set that's just a plain CSV, and one of the columns might say county, or maybe country. And you know that it has a geospatial component, but then since it's not a geospatial data format, you can't visualize it using the techniques from the previous lectures. The issue is that if you had something that's like, state equals Wisconsin, R doesn't know by default the location of the boundaries of the state, right? And just reading in a comma-separated file where one of the columns has a value saying Wisconsin or Minnesota or Michigan, that is not telling it any of this important vector information saying like geometrically what are the shapes of these states, right? So just from that kind of CSV, you cannot make a map. But what's really handy is there are a bunch of packages that allow you to link those just name-wise, like plain data frame type formats with vector information giving these sort of boundaries or giving these geospatial coordinates that you need in order to make a map. To illustrate, using the RNaturalEarth package, you can get the boundaries of all the counties for Wisconsin in a spatial data frame, kind of a polygon format. So just using the same TM shape type code from before that we used for polygons, this is showing all the counties in Wisconsin. The same package is actually quite more general. So this is for counties. You could have done the same with state level. You could have done countries, continents. I think you can even do census tracts in the United States. Another kind of very commonly used vector data source is the American Community Survey. So this is in the ACS package. American Community Survey is like the census, except it's even more frequent. So in this call, I've gotten this one variable is household income. So I'm showing the average household income for every single census tract within Dane County. And when I use this package, it doesn't just return a CSV file saying, here's census tract 1, census tract 2, and the income. It's actually returning a geospatial data frame. So I can again use TM shape, and I'm able to see now the average income associated with every single census tract within this county. Okay, so that's kind of the first set of tricks, is even if your original data might not have a geographical component, it's very easy to get new vector data formats using these public packages. Second trick. Sometimes you might want to work with several geospatial sources at once, and you might be trying to overlay the layers, and you might get very strange behavior. You might be seeing that regions that are supposed to be overlapping, when you try plotting them, they look like they're on very different locations on the Earth. The reason this sometimes happens is because you might be using a different projection system for each layer. What a projection system is the Earth is 3D, but then whenever we make a map, we're trying to put it onto 2D. And there's actually no unique way of taking that 3D surface, plotting it on 2D, and not creating some sort of distortion. Right? So there's always going to be some changes in the lengths, some changes in distance, some changes in area that is introduced when you project from 3D to 2D. If you stored your data set with two different projections, then that's going to cause this mismatch when you try overlaying. So you might not have noticed in all the read SF and Terra calls in the previous lecture, but they always printed out something called the CRS, or the projection field, associated with each dataset. The CRS is the coordinate reference system. It is just a terminology used to store the projection. We will almost always use something called EPSG 4326. This is kind of a universal projection system. It's the one that Google Maps uses. It's kind of a reasonable default. But if you notice that things are not matching, you should try to see whether they're actually, in fact, in the same reference system. If they're not, you can transform them. So there are functions in both of these packages that allow you to change from whatever the current one is to 4326 or any projection you want. If you get into this issue, just send me a message. Okay, that's the second trick. The third trick. So you've almost definitely seen something like a choropleth. It's like this. You might not have seen something called a bivariate choropleth. So a bivariate choropleth is a version of a choropleth where you're trying to plot two variables side by side. It's kind of the multivariate dynamic. So just maybe to understand what it looks like before we look at the code, this is plotting obesity rates versus diabetes rates. The idea is that if you have very high diabetes rate but relatively low obesity rate, you end up in this kind of dark blue color. If you have very high obesity rates but low diabetes, you end up in this kind of dark red color. If you have high of both, then you're here. Okay. So that's what you get in this figure. I'm actually able to see relatively few of these high obesity, low diabetes, maybe a couple, right? Relatively more of these high diabetes, low obesity. Right? But these are generally correlated. Right? I think that's like the main thing that you find here. It's like these two typically have the most. So it allows you to see correlation in these two spatial variables that would be really hard if you were just plotting two choropleths right next to each other. How is this implemented? Right. Here's just reading the data. I've categorized my two kind of continuous obesity and diabetes variables. I've joined it with the same kind of counties data that I showed earlier. So this original data set is just rates. It's just a CSV file. I've joined my CSV file with my vector data information in the counties. There's some small processing about the codes. I think I didn't want to have Alaska or Hawaii because that would have created a big gap. And then finally, I'm using this GeomSF, and this is what's creating the bivariate choropleth. Right? Biscale fill is an addition that you can use for. This is actually a ggplot, a spatial format. So we've been mainly using tmap, but you can do a lot of the same thing just using ggplot. It's a little bit extra writing, and it's not quite as automatic, but you can do it using ggplot. And if you want to use this scale fill function, which is what allows you to do the encoding for the two different colors simultaneously, then you have to do it using the GeomSF approach rather than the tmap approach. Okay, so that's just creating the bivariate choropleth. Here is defining a legend object, and I'm saying to put the legend in this location. Okay. So a last point, it's a pretty common situation to have spatiotemporal data. So you have something evolving on space, and it's changing over time, right? Some people say you should do something like this. This is called a time cube. So there's kind of a neat plot. You can kind of see that this point this is the trajectory over time. It's moving along the map. But we will generally avoid 3D in our visualization class. It tends to be, usually only want to use 3D if it's absolutely necessary. It's often possible to get the same effect using just 2D. But in order to do it well, we're going to need some sort of interactivity. That will be the topic for next week.